Hello, my name is Kaya Mitchell, and today I'll be presenting my Lab 3. Orbiting objects are objects who are only acted upon by gravity. The force which governs their motion is the gravitational force of attraction to the object which is at the center of their orbit. Gravitation is a force which acts over large distances and in such a manner that any two objects with a mass will attract. An orbiting object is accelerating, where its velocity is changing, either the speed or direction. The net force acting upon such an object is directed towards the center of the circle. The net force is said to be an inward or perpendicular force. In addition to the perpendicular force, a parallel force is acting upon an object who is changing speed, and this force vector is parallel to the momentum of the object. In this lab, we will apply Newton's second law to find the mass of a black hole by using a star's known mass, initial position, and trajectory motion around this black hole. The answer to this lab is important because black holes provide an important tool for probing and testing the fundamental laws of the universe, where all objects exert an attractive gravitational force which depends on their mass. This concept intrigues everyone, especially physicists who theorize about the nature of matter, space, and time, and also astrophysicists who look for real black holes out in space. The results of this lab prove that it is possible to predict the mass of a black hole by modeling a star's known motion around this object. To get our computational model started, we first set the appropriate initial conditions as seen here, where the gravitational force constant is as shown, the star's appropriate mass, which was given to us in our starter lab, and the value of each time step was set to the value of seconds in 1 day, and our time started at t equals 0. Once these variables were added, we then applied the momentum principle to find the initial and final momentum by multiplying the star's mass by the initial and final velocity. That was then used to find the rate of change in momentum by subtracting the initial and final momentum and dividing it by our time interval. And according to Newton's second law, our F net is equal to the rate of change in momentum, which is dp over dt. We then need to find the parallel and perpendicular components of force. To do this, we first had to find the unit vector of momentum, which is equal to the initial momentum divided by its magnitude. To find the parallel component, we first had to find the change in magnitude of the parallel components and divide that by delta t, and then multiply that by our p hat vector, which will represent the change in momentum, thus also representing our change in velocity, since F net is equal to dp over dt. We then set F net parallel equal to dp over dt parallel. From here we can subtract our dp over dt from our dp over dt parallel to find the perpendicular component, since the total change in momentum is equal to the sum of the parallel and perpendicular components. And finally, we set F net perpendicular equal to dp over dt perpendicular, as they are all equal. Now that we have all of our components calculated, we can now solve for the mass of the black hole by using our gravitational equation, where the mass of the black hole is equal to F net times r squared divided by the gravitational force constant and the mass of the star. And as you can see, the mass of my black hole came out to be 1.42 times 10 to the 34 kilograms. And from my computational model, you can see that as the star moves around the black hole, the perpendicular force points towards the center of its circular path, no matter the position of the star, and the parallel force points in the direction of motion. And both forces get larger as it gets closer to the black hole and smaller as it moves further away from the center of mass. Now let's answer some questions. How does the net force and its parallel and perpendicular components differ from the rate of change in momentum and its parallel and perpendicular components? Numerically, both the net force and change in momentum are the same. However, the net force is what causes the change in momentum. So the net force is equal to the change in momentum, where a non-zero force causes an acceleration, which is the change in velocity, and thus a change in momentum. But they are not the same thing. Where F net, you use Newton's gravitational formula, or the sum of forces acting on the object, whereas for the change in rate of momentum, you will use the change in velocity. Now, if you were given the same position and same motion observed, would you be able to calculate a different mass for the black hole? No. The mass of the black hole cannot be calculated given that the motion and the location of the star did not change. There would not be a different gravitational force in order to calculate the new force of the black hole. But overall, the idea is that we were given the same initial motion and initial location of the star to calculate the black hole's mass. And if these values remain the same, then we would not be able to calculate a new mass. Thank you so much for learning physics with me, and I hope to see you next time. Bye!